white matrix, which will give you the outputs corresponding to the class of the output. So the advantage of using this kind of a network is that given the set of inputs, ANN or artificial intelligence is consistent in its prediction. But consistency is good, but consistency is not everything that we need. For example, suppose I show you this picture. It is all fire only. But the kitchen fire has to be treated differently from the fire on the house. So that is the difference that you need to consider when you are having classification. You only need, it is not sufficient that you say that, oh, this is different thing. Wait, this is not correct. Okay. So fire in the kitchen is to be treated differently from the fire in differently from the house on fire. Well, one of the ways in which usually this kind of problems are addressed is by looking at a bag of words. So suppose you want to analyze a sentence or a script, what you do is that you look at the words that are used. Somebody uses the word bad, then you note it is taken as a reaction from the user as this particular thing is not good. If somebody says excellent, then it is taken as a good. So it's a method called bag of words. But the problem with bag of words is that it does not preserve the order. For example, if somebody says the food was good, not bad at all, it has the same number of words. Food is there, bad is there, good is there, but it totally means, the meaning is totally different. So you want to have a condensated information in addition to the bag of words to decide whether something is, is correctly input. So that is a challenge. Then we also need to learn, so you need to learn the context, and in addition to that, we also need to learn the sequence in which the events are happening. For example, context is history and a list of events as a function of time. And function of time means you need to have the history. So you need an entirely different type of network other than the neural network for doing your analysis. Well, we are all familiar with Markov chain model, where you have this kind of this facility available. But Markov chain is trained in a different way, learned in a different way, and we want to implement something similar to that using the machine learning neural network tool. So something similar is available, which is called the recurrent neural network. What recurrent neural network does is that, along with the input, it keeps a copy of the past and use that also for the prediction. So you have a sequence of networks. This one learned, then that is carried over to the next network. This carried over to the next network, and like that, so that you have the history also recorded. Well, so this is how it works in the feed-forward network. In the standard neural network, you have the input, you have the effect, and you have the output. But in the recurrent network, you take the input back to the we take the output back to the input and keep on monitoring the sequence in which this is occurring. In fact, although it is drawn like this, it is yes, it can be yes or no, it can be classes also. For example, I am giving here some different examples. If your answer is yes or no, you need only one output. So whatever output you get, wherever it is, suppose you have 9 outputs coming out, wherever it's a 1, you say that when this is the input, this was the output. So you have only one output that is to be taken. And if you have 9 outputs, you say that all others are 0. This one is only 1. So likewise, we can treat it as a multi. So here it is a 1-to-1, which means that you input one output, one input, you get a one output. Here it will be 1-to-many, where you keep on looking at the history, and each time you give an output. Or it can be a many-to-one, you keep on looking at the sequence and say that, oh, this is a dangerous situation. So you see a person moving, and if you see that he is going to a particular place where he is not supposed to be present, then immediately you send an alarm. So this kind of monitoring kind of things can be done in astronomy also, where you observe a particular object and you expect something to happen, and as soon as it happens, you send a telegram to the astronomer saying that, oh, that event has happened. You just take the image. Or it can be many to many, or like this. Okay. Is it clear? Am I going too far? I hope these are simple things. Okay. So, but the problem with the recurrent neural network is that it won't be able to preserve data for a long period. If you want to keep the data, suppose I say that I was in US and at a later time I say when I went to France, you need to connect my US trip and also my France trip, and then has to based on that you have to inform. We humans do it very easily, but for machines to do it, it is not that easy. So you find that you need long short-term memory for doing that, and that is the kind of network we use for most of these NLP kind of problems. What you have here is it can recur and keep long-term dependencies, and it can also control the flow of information, meaning that you can remember something, you can forget something. All these things are digitally controlled. Again, I do not go into the details of this topic because of the time constraint. What we need to know is just what I am saying. But if you look at the internet, you can find several tutorials which help you test what LSTM is. Well, so here, suppose I have a sentence, Mary went to school with Bill. Then I want to extract the information contained in it. So each word goes to an LSTM, and each word is recorded and stored. And if I ask, where did Mary went, the network should be able to say she went to school. Or to Miss Mary went, it should say with Bindu she went to school. Likewise, it should be able to answer questions, and these are already done. And that's exactly how Google answers the question. So whatever question you pose, Google will give you the correct answer because it is able to do this kind of analysis. It is a very interesting and simple problem, and there are ready-made tutorials and software available for doing that. One of the languages I recommend if you have not learned is Python. Because almost everything is done in relating to this is done in Python language, and Python gives you the flexibility. Python gives you the flexibility to use all these things in a very convenient manner. Now, if you look at the examples that have been used using NLP, this natural language processing system, you find a lot of applications, including what Google does for categorizing your email into different groups, to detecting spam, analyzing TV. For example, sentiment analysis is one of the things that you usually do with NLP kind of thing, where you, without watching the movie yourself, you ask the machine to watch the movie and tell you whether it's what kind of movie it is, whether it's having some sentimental connections to which we can correlate it with all these things will be analyzed by the system. But coming to astronomy, I just want to give you one example, because there are many examples which I can point out, but this is just one example, which is an application which was developed by Shilu and Nikhil, who are two postdocs at IUCA. Shilu was my PhD student also earlier. It's called LIGO. LIGO is the gravitational wave observation, and it uses you can see here I go into this particular website if you want to do that. Gravitational wave detectors use interferometry for doing the classification for detecting gravitational waves. These interferometers have very long arms, about 4 kilometers in length, and it has very precise optical arrangement which allows you to classify, allow you to detect even small variations in space. So this is the structure. So it uses a laser beam, it's a laser interferometer. So it uses a laser beam using a mirror, it splits into two, and if there is no vibration, no movement in the arm, then you see that the light goes to the same distance, comes back here and produces black fringes, which means that there is no interference. But when there is a gravitational wave coming, there will be some kind of oscillation here and here, which will be, because they are orthogonal, which will be different, and that will produce some changes in the frequency here, which you can implement the kind of gravitational wave activity. This is a very tricky problem, and the precision with which you need to keep these mirrors, floating mirrors at this distance is really difficult, and you have lot of sensors. In my heading I said I will talk about Internet of Things. Internet of Things is nothing but sensors which you have on your machines. For example, whenever you Google or whenever you search for something, it is a sensor that that monitors your interest, the kind of locations you usually look at. All this information is used even for language processing. But this is a different kind of sensor. These are all very small sensors which will keep on monitoring, and there is a feedback system. There is a feedback system which makes sure that all the mirrors are aligned properly whenever there is no external activity. And this is done using some noise generation, which is usually done for analyzing the. So the same input is given to both those mirrors, and you see whether it cancels out the noise. I mean, there is no interference pattern that is generated, then you say that the mirrors are properly aligned. And when you give different values, it should produce the corresponding. So that way you analyze the sensitivity. Now, what HairLiGo does is, this is a big project which involves about 2,000 engineers who are continuously monitoring the whole thing. And it is very difficult for them to communicate with each other and say, oh, I have found a problem here, that problem has to be fixed, etc. So what they do is that they put a law. And you are expected to go through all these laws before you make an observation, which is practically impossible. So what HairLiGo does is, it automatically goes through the laws they have put in natural language. It interprets it and tells you whether the particular observation that you have taken is valid or it is wrong. So that is the kind of thing that HairLiGo does. So it has various. So every day it tells you what is the trend, and it will tell you what is the positive summary of the particular situation as well. Well, then there are calibration issues. You need to know whether the calibration is proper. So for that also, they keep on writing laws which you go and put. And that is this is a program that is now running on LIGO, and it is very efficient because and it is very much appreciated. That's the reason why I present this, because it helps the astronomers to yes, recently we have tried in a different language, for example. Yeah, so it all has to be taken into consideration. There, when I was saying language, Jay was mentioning, it has some jargon which they use, which has to be explained. Everybody tells in English, but jargon has to be interpreted. So that is a difficulty which has been faced. Okay. So these are the sensors that are used. I do not want to go through that, but you can see that there are more than 100 sensors which are being monitored, and each one has a specialist who is dealing with it. So that's all that. Well, then, okay, the suspension of the mirrors also has to be monitored, and that information also is available online to this particular site. I would recommend you go to HairLiGo and just Google for HairLiGo, you will find that. And it is very interesting, especially for those who are doing instrumentation. Well, another issue is the wind. All this LIGO, there are two LIGO instruments now. All these LIGO instruments are kept in seismic-free areas, which means that you don't expect any movement on the surface of Earth, but there is wind, and that can create a mirror too, and that also has to be taken care of. So these errors are usually termed as glitches. And Tarun was asking whether it is possible to have a limited number of features for doing the classification rather than going to deep learning. In some cases, it depends upon the problem. In some cases, it is wider that it goes to limited number of features. For example, in this particular case, this again was done by Shiru and Nikhil. These are the different kinds of glitches that come. Glitches means they are noise coming in the data, and this looks very simple here, but the problem is that these glitches also look very much similar to the gravitational wave detection that what we are going for. So it's very difficult, especially in real data, because when it comes to real data, this is how the glitches are. They are not easy to be detected because the signature noise is very. So whenever the noise level is very high, most of the deep learning neural networks fail, and they fail catastrophically because they have no ability. They are filters, but they have no ability to distinguish noise from real data. So most of these deep learning networks, if you look at the images, you find that most of the images are very good. You can see whether it's the face of a human or whether it's the face of a doggy. So that way you can distinguish. But if you add noise to it, it becomes really difficult. And that's one of the things. So what Nikhil and Snehanshu did is that they found out some wavelength-based analysis, wavelength entropy, that can characterize each type of glitch into different forms. So they just calculated into wavelength space, did an entropy, and used it. And this happened to be the first machine learning for real gravitation waves. So this is also being used because look at the accuracies they get: 99.8, 99.7. This is 100%, 99.4. So all of them are close to 99. So that is the accuracy with which now glitches are being removed from the gravitational wave data, and that means you get much more sure. Okay. Now, what IoT application is there which keeps on monitoring the specific activities in the region or the user recorded. If something happens, immediately alerts us and don't return the data and things like that. Just as you gave example. Okay. Now coming to SKA, the square kilometer array of which I mentioned before, which is being built. SKA has a miniature version of it which is called the Meerkat. So when Meerkat image came, there were several extended objects seen in the image that in fact classified in different groups by the radio astronomers. And Arun Kumar was also a PhD student of mine, but he moved over to square kilometer array and a postdoc student. What he did is he wanted to find out which are the sources and which are not. And if you look at the sources and the artifacts, you immediately notice that it's not easy to, even for a human it is not easy to identify. So you need to consider several other details, parameters, which can tell you whether it's a source or not. So when he tried different networks, he found that convolution neural networks gives him the best result. Still it is 99.0%, which is not the, we would like it to be 100%, but it is better than what it is. So I think I would summarize here. Good science requires good data, and deep learning tools usually offer several reliable methods. I did not go into all of them, I just went through one because of time constraint, plus because of human expertise in computing power to produce it. So I would rather it looks at both the language spoken, then it looks at the grammar that language uses, it looks at the expression on the face, it looks at the location where the person is looking. Oh yes, the whole video is sent to the thing, and based on that it gives weightage to it. You make the video into different frames. So you take each frame, then you take the differences between the frames to see movement. And if it is a static, it won't bother about it because it will look the same in all the images. So it knows that it is not a moving object. But whoever is doing it takes the differences to find out the difference. And it looks at the frames to So what your husband on the page, immediately your husband can say, oh, he's sad, oh, he's very happy, or something.
So the old style of doing astronomy was actually after pushing and then you for after and you write specifically like the sea observation. Now you have the zero observation. Is it actually going to happen that the neural network will actually point out new and good things?
Yes, absolutely. That's the reason why we do it. See, we are not interested in same kind of object. Suppose I see a million G-tech stars. I'm not interested in that because all of those G-tech stars maybe there is something different or else from the larger majority of the stars in the galaxy. But suppose I happen to see something different. So with all these things, all the ideas mentioned there is an associated possibility. So whenever you say that a particular object is belongs to a class, it's like I have the confidence it is 50% likelihood of that particular class, 50% likelihood of that class. So when you see that there are multiple classes which are predicted with some reliable confidence, below some reliable confidence, you immediately count those ones. So that leads you to discovery and which may be of more interest and also
so that's just a beautiful outlier.
Yes.
I may take to restrict what's the potential that is actually not just over to the outlier and
yeah, it depends upon it depends upon how you are going to use it. Because the HR diagram was considering the simple case. Let's put it into a straight line, but you see that it is broader enough or it gets bounded. So you have to apply a physics and then find out why it is happening. So whenever you are doing machine learning also you will find that maybe that's about you discover the thing. Yes.
I want to ask what are the future applications of gravitational detection?
Yeah. This is a very difficult question to answer because it's being developed. And when radio was first made, when the radio signals were transmitted, nobody thought that there would be a radio. So it is a principle. We expect that gravitational detectors will let us have a much more wider application, but maybe after my time, maybe in the next 20 years. Okay.
Hello. 304 and 301 is 35.